And then I'd say, take it away.
Great. Well, thank you so much for inviting me for this awesome, exciting opportunity, Laura. And also, thank you very much for that really nice introduction there. I'm going to go ahead and share the screen from my end. Hopefully works without a glitch. You'll see my screen there. Great. Okay, so today I'm really excited to share some of our recent work examining, I call a dilemma of visual working memory. So as we all know that our environment is visually rich. So let's assume that you just finished a long day of work. And then on the way home, your wife calls you and say, hey, can you pick up some produce from the grocery store, right? And you just stop by at the grocery store, and what welcomes you is this colorful display of produce, right? But your job is not just simply be amazed by this color, right? Your job is to remember what you need to pick up on the way home, like say tomatoes, and you need to find it using your memory representation of the tomato and the perceptual information that's in front of you, right? You successfully pick up the tomato and you go home. And then as soon as you open the door, your kid dashes to you asking to play with his favorite picture book of Where's Waldo. If you have done this picture book before, it's essentially a really tough visual search task. You need to find this guy with a red striped shirt on this really cluttered display. So here again, your job is to represent what that guy, Waldo, looks like in your mind and use that information to navigate to complete your goal of finding that guy in this display. Once your kid is satisfied and you eat the dinner, you have a little bit of time to relax yourself. So you walk up to your bedroom and then you turn up your favorite video games. And here again, you're now constantly bombarded with a dynamically changing visual information. And here your job is to find the guy who you are attacking and hopefully shoot them while not shooting your team players, right? And when you're satisfied with that play, then you realize, oh shoot, I forgot to prepare the slides for tomorrow's lecture. So now you frantically go up to your laptop and open up your laptop. And what you see is this cluttered displays of folder if you're like. And here what you gotta do is to find the folder that says class and start preparing the slides. So no matter what slice of life you take, what you're constantly challenged is to deal with this massive flood of visual information. And here, to behave in a goal-oriented manner, what you have to do is to selectively represent task-relevant information at that time in your mind. Fortunately for us, our mind is equipped with visual working memory, an online mental workspace. This visual working memory allows us to represent or actively maintain visual information in readily accessible state to perform the goal-oriented task. So in that example of grocery store, you need to represent what tomato looks like and then find the tomato by comparing your mental representation with what's in front of you. Okay? The past studies have examined this mental workspace, primarily focusing on the characteristics during maintenance. Okay? One way to study working memory is by doing this right now classic, some people might say outdated task called a change detection task. In this task, participants are presented with an array of simple objects for a brief period of time. Usually people use something like a simple colored squares. And after that brief display, screen goes blank for a short retention interval. And after that, participants were presented with one item on the screen. And the task at this point is to compare this new item to the representation in their mind. If it is the same item, they would say it's the same square. If they think it's a different item compared to the item that was at that location, they would say it's a different item. Given the simplicity of this task has been adopted to study visual working memory across lifespan, right? This task has been used with kids, older adults, even for a different species than humans to study working memory. If you were to do this task with healthily developing young adults like college students, what you find typically is following. Here, what I'm going to show you on y-axis is the accuracy of that change detection task, and x-axis is a set size or the number of colored squares displayed for you to remember. Right? When the set size is below 3, people do fairly well, right? Accuracy is right at the ceiling. However, once you go beyond that set size of 3, the accuracy monotonically declines. The reason why this task was adopted widely is that with a few set of assumptions, you can estimate how many colored squares worth of information must have been stored in order to achieve this accuracy function. So if you were to do that calculation to compute the working memory capacity, or how many colored squares were stored in memory for each set size, what you see is this, right? The capacity estimate will rise up until set size 3 or 4, but after that, no matter how many more items you add on the display, the capacity estimate remains relatively constant, right? Sorry. So based on this robust finding, researchers argue that our working memory capacity is severely limited to about 3 to 4 colored squares worth of information, right? Although many researchers do agree that our capacity is limited severely, there's still an ongoing debate as to how this limit should be characterized. Some people argue that this capacity limit reflects a discrete item limit in how many items we can hold in mind, right? We can hold about 3 or 4 things in mind. Other camps would say, well, no, the capacity limit should be better characterized as the pool of continuous resource, right? In theory, this continuous resource can be divided into infinite number of items. It's just that, the amount of information in that pool is limited. Other people might argue that this capacity limit is the product of interference from the other information in memoranda or information from the past and so forth. And most recent work will say, well, this actually reflects your ability to tease apart the confusion between what you remember and the other information, right? So all these theories are still debating as to best characterize the working capacity. And some people even argue that it's a combination of multiple effects, right? Another interesting thing about this visual working memory is that there's a wide range of individual differences. Here, what I'm going to show you is a histogram that we collected from about 500 university students, right? And what you can see here is that the mean is right around 3, but at the same time, there's a wide range of individual differences. Some people can remember more than 4 or more colored squares worth of information, whereas others can remember 2 or less colored squares worth of information. And interestingly, this individual difference is reliably related to a wide range of higher cognitive functions, including fluid intelligence. Here, what I'm showing you is a simple scatter plot between individuals' working memory capacity and their performance on a fluid intelligence measure, in this case, Raven's Advanced Progressive Nature Series. So given all these findings, it makes sense that the researchers have been primarily focused on characterizing the quantity and quality of representation that can be stored in working memory. However, that only paints a picture on one aspect of visual working, right? Visual working memory, the whole point of this is that it is a system that supports our goal-directed behavior. So today in my talk, what I would like to ask is this questions. What happens to working memory when it is used for a goal-directed behavior, right? If you were to understand this working memory, the online mental workspace, we need to know what happens to working memory when it's served its purpose, a goal-oriented behavior, right? Just to illustrate that point, let's consider the following example. Imagine you are walking on this really busy street and waiting for the signal to turn green. And right at the moment when the signal turns green, you realize that the guy in front of you drops his phone from his pocket. As a good citizen, you'd run up to that phone so that you can return it, right? But the moment that you look up on the street, you realize that that guy took off without noticing that he dropped the phone, right? So now your job is to try to remember what that guy looked like so that you can find him through the comparison between your working memory representations and the perceptual information that's in front of you. Okay? Here, in order for you to successfully return that phone to the guy who lost it, the assumption is that your working memory representation of this person remains intact as you compare it with the information that's in front of you. Okay? Does it stay intact when you use your working memory for goal-directed behavior? Well, to test this in the lab, we can't keep dropping the phone because we don't have enough funding to do that, right? So my former undergraduate student and myself conducted the following experiment. In the baseline condition, we presented one color patch to remember. And after a short retention interval, we presented a color wheel and asked participants to indicate the color by moving this aligned segment to best approximate the color that they just saw. After they picked the color on the color wheel, we presented a color patch with the selected color and asked them to fine tune the color so that they can be satisfied with the accuracy of their report. Once they are satisfied, we ask them to report their confidence in the accuracy of the report, from high confidence to no confidence. Okay. Together with this baseline trial, in the critical perceptual comparison trial, we presented an intervening probe during the retention interval. And when they saw this intervening probe, what the participant had to do was to report whether this probe is similar or different compared to the original item. Okay. So they have to say whether this is similar or not compared to the original item. After they make that perceptual judgment, participants were asked to report the original item using the same procedure, along with the confidence in their accuracy. Okay, so here what I'm going to show you is the distribution of response offsets for the trials where a participant indicated high confidence in the accuracy of the report. Why? Well, what we wanted to make sure is that we are looking at when the trials, when your working memory is working great. You don't want to contaminate the data based on the trials where they lapse attentionally and they don't have a really good memory of the original item. That's why we focused on the high confidence trials. Okay. So when we look at the response offset distribution for high confidence trials in the baseline trials, what we found is a really nice tight clustering of response offset around the actual target count, showing that the working memory representations are fairly accurate. Now, what I'm showing you here on the gray, in the gray is the range of the probe distance that we presented in the critical conditions. So the probe that was presented ranged anywhere from 16 to 105 degrees away from the target color. When this probe was judged to be similar, what we found is a reliable shift in the response offset distribution in the direction of that probe. On the other hand, when the probe was judged to be dissimilar, what we found is a much weaker shift. Just to quantify the magnitude of this bias, we computed the mean response offset so that the positive value indicates the response offset in the direction of the probe. When the probe was judged to be similar, we found a nice reliable bias in the direction of the probe. But when the probe was judged to be dissimilar, the bias was much more attenuated. So what this result seems to suggest is that perceiving new input that's similar to working memory attracts the representation to that similar looking input. Okay? At this point, you may be wondering, is this driven by simply the physical similarity of the probe? Or is there something psychological about this? Maybe it's the perceived similarity as opposed to the physical similarity. One way to get at that is to control for the effect of the physical similarity by looking at something called the ambivalent probe. Okay? We define the ambivalent probes as a probe whose distance from the target was sometimes judged to be similar, but another time judged to be dissimilar. Okay? That way, we are looking at the physically identical probe distances. And if we see any difference in the magnitude of the bias, we can say this is not the effect of physical similarity of the probe, but the perceived similarity of the probe. Here I'm showing you is the range of the ambivalent probe. When the ambivalent probe is judged to be similar, what we found is a reliable shift in the response offset in the direction of the ambivalent probe. And here is the magnitude of that bias. When the physically identical ambivalent probe was judged to be dissimilar, what we found is the lack of such bias. So what this means is that this similarity-induced memory bias is driven by the psychological perceived similarity of that probe. This is concerning, right? We need to keep the memory representation accurately across the use, right? Because if we can't do it, we may not be able to return the phone to the guy who dropped it. So what we wanted to then do, or April and I wanted to do, was to find a way to cancel out this memory bias. And our approach was to ask people to do additional similarity judgment so that we can correct the once distorted memory in the right direction. So to do that, of course, we had the baseline trials where participants simply remembered one item over the retention interval. And after that, we asked them to report the original color along with the confidence. We had two types of critical conditions. One of them was called same side probe condition. And I'm going to explain why I call it same side probe. Okay? After people hold one item in working memory, we had participants do a similarity judgment. In this case, we presented a pair of probes. Just to illustrate how we selected this probe, please take a look at the color wheel over here. Okay, if I was to plot to indicate where we chose this color, you can see this bidirectional arrow, right? One of the items in the pair was picked close to the target, and the other one was 180 degrees away from the physically similar probe. So here the participant's task was to pick which one is more similar to the target item. After they make that judgment, we ask participants to do another perceptual judgment by presenting another pair. Again, if I were to plot how we selected this pair, you can see this dotted bidirectional arrow. As you can see, the physically similar probe in the second judgment was on the same side of the memory item as the first similar item. And this is why we call this condition the same side probe. The similar item in two pairs was coming from the same side of the memory item. After people make that two judgment, we ask people to report the original item along with their confidence in the accuracy of the report. In the other critical condition called opposite side probe, some of you might already know, guessing what's going to happen, but I'm just going to walk you guys through it. After participants hold one item in working memory, they did one perceptual judgment, right? But in the second judgment, we sampled the probe pair in the following map. We chose the similar one from the opposite side, right, of the memory item. So now it's on the clockwise side, the similar ones. After doing these two judgments, participants reported the original color along with the confidence. So here what I'm showing you is a response offset distribution for the baseline condition. And that gray area here indicates the area from which we sampled the first similar probe. In the same side probe condition, we successfully replicated the previous finding such that perceiving a new input as similar biases the working memory representation in that direction. Interestingly, when we have people go through the opposite side probe, sorry, I forgot to show you the magnitude of the bias there. Interestingly, when participants judge the opposing side of the probe to be similar, we were successful at canceling out that bias. Right? So what this shows is that, yes, the similarity-induced memory bias can be canceled out by additional similarity judgment, by biasing the memory in the opposite direction. Okay. Next, what we wanted to do is to get at the computational basis of the similarity-induced memory bias. Here we contrasted two potential mechanisms. One is called representational integration, and the other is called probabilistic confusion. This is the work that was done in collaboration with Causal. So let me walk you through what I mean by representational integration. Let's assume that this is the memory representation of the original item in memory, and this is the representation of the probe item. When people judge the probe item to be similar, what happens is that these two representations, the original memory representation and the probe representation, gets integrated in forming a joint density. And this becomes now how people make a report. Okay, so that's the representational integration mechanism. Alternatively, people may have original representation in black and the probe representation in blue independently, but at the time of report, people might get confused probabilistically, and sometimes by accident make the report based on the probe representation. If that's what's driving the bias that we observed, we should expect to see the bias offset distribution to look like this, shown in red. Okay. So our approach to tease apart these mechanisms was to make these computationally produce these models and find the best fitting parameter. Okay. So here, what I'm showing you is the observed data, the response offset distribution when the probe was judged to be similar. Here, what I'm showing you is the best fitting joint density model with a representational integration model. Okay. Now let's contrast this to the best fitting mixture model. Okay. I think it's very clear that which model is winning to approximate the human data. Right? The JD model seems to capture the most of the really core characteristics of the human data, whereas the mixture model doesn't quite do that. The mean is right at the red line, and bias is introduced by a fatter tail in the direction of the probe. So, just beyond just simply looking at the data subjectively, we also formally compared these two models, and what we found is a unanimous win of the joint density model across all the fit statistics. Okay. What's cool about this JD model is that it can also predict the magnitude of that memory bias across different ranges of probe distance. So here on the x-axis, I'm showing you the human memory error for each probe distance that's shown in different dots on the scatter plot, and y-axis is the predicted response error from the JD model. Okay, so this is all good, but we wanted to get a further empirical support for this model. And here we tested the following hypothesis. If the JD model is correct, people who show a larger bias are those who have less precise memory representation. Why? Well, if your memory representation is less precise, your representation has a larger width. Right? That makes it prone to create an overlapping representation with a further away probes. Okay? So we tested that by gathering people's memory precision and the magnitude of the SIMB. And here what we found is a nice negative relationship between people's memory precision and the magnitude of the bias. So this provides empirical support for the representational integration. Okay. So far, we've shown that when people see something similar, the working memory gets biased in that direction. But is the similarity judgment, the goal-dependent use, is it really causally manipulating the magnitude of the bias? People might say, well, there's the same thing happen when we tell people to simply ignore that probe, right? Because if you look into the literature, there are many cases of memory attraction induced by a task-irrelevant distractors. So my current graduate student, Joseph Saito, wanted to tackle this question directly. So in his experiment, he had the baseline conditions where participant had to simply remember that color patch, but he mixed this baseline condition with another trial in two different tasks, in two different blocks, sorry. In the ignore block, when participants saw this intervening probe, we told them to simply ignore that intervening probe. Okay? In the other comparison block, what participants were told is to compare the intervening probe to the original item. Okay? Notice that the ignore and compare these two trials are physically identical up until the report of the original item. The only thing that was different is whether they have to ignore the intervening probe or to use that probe for the perceptual comparison. Okay, let's take a look at the result. Here, what I'm showing you is the distractor-driven memory bias in the ignore conditions, okay, across different probe distances. If the goal-dependent use modulates this memory bias, then what we should expect is an increase in memory bias in the comparable ones. And that's exactly what he found. Okay, so what this shows is that, yes, this goal-dependent usage of the memory seems to modulate this bias. Next, he wanted to revisit the idea of the perceived versus physical similarity. And to do that, we use the same approach of isolating the ambivalent probes. Here, when we look at the magnitude of the bias induced by the ambivalent probe in the ignore condition, there was a small but reliable shift in the direction of that probe. If the perceived similarity modulates this bias, then we should expect a larger memory bias following the similar judgment for those ambivalent probes, but not much of a modulation when people perceive the ambivalent probe to be dissimilar. And that's exactly what we found again. A larger memory bias when the ambivalent probe was judged to be similar, but equivalent bias when that probe was judged to be dissimilar, as when that probe was ignored. So this result nicely demonstrates that this is driven by the goal-oriented use of working representation. So far, we've been showing this using relatively simplistic stimuli, colored circle, right? We also replicated this with a geometric shape, but still, right? Does this only happen with a simplistic lab stimuli? So Joe wanted to test whether we can find the SIMB with more complex real-world stimuli. And the stimulus of choice was a real-world objects. So here, what I'm depicting you is the baseline trials. Participants were presented with the colored real-world object, and they have to report the color of it along with the confidence. In the critical condition, right, we replicated the design of the same side, opposite side probe condition. So just to reiterate, during the retention interval, we presented a pair of probe items and asked people to pick which one is more similar. And we had people do that twice before they reported the original color along with the confidence. Showing you the response offset distribution for the baseline condition. Here, this is the first similar probe distance. In the same side probe condition, we replicated the systematic shift in the direction of the similar probe. That's the magnitude of the bias. In the opposite side probe condition, we see no such bias. So again, we were able to demonstrate the SIMB using more real world stimuli, and we were also able to cancel it out. Okay, you guys might be wondering, well, sure, you use a real world object, but still the memory was about the color. What if you modulate the similarity more holistically using more complex stimuli like faces? And that was the work that was done by my former thesis student, Jared Tell. So here, participants did a face working memory task where we presented an artificially generated face and we asked them to remember it as precisely as possible. And after that retention interval, we presented a face wheel. Sorry, it's a little hard to see here. And people had to report what was the original color using this face wheel. And after that, they reported the confidence as well. In the critical condition, a face was presented, but during the retention interval, we presented a pair of probe faces. And here, one of the probe was 45 degrees away from the original face that you see here. And the other one was 180 degrees away from the target face. And after that judgment, they reported the original color, along with the original face, sorry, along with the confidence. Here, since we wanted to test it in an inclusive way, we generated these face wheels for all the races that we were able to create the face using a software called FaceGen. There were 4 racial categories in that face generation application: Africans and Europeans or Caucasians, East Asian and South Asians. We would love to increase the palette as more races becomes available for a generation of the face stimuli. But anyhow, we also, created separate wheels for male faces and female faces. Let's see whether the bias occurs for all kinds of races. Yes for African faces, yes for East Asian faces, yes for European faces, and the South Asian faces. So regardless of the races, we are able to induce this SIMB or this complex stimuli. Okay, so just to summarize what we've talked about so far, Visual working memory can be biased as a consequence of its usage in perceptual comparison. And this bias occurs particularly when your working memory is compared to subjectively similar input. And this similarity-induced memory bias happens when people remain highly confident in the accuracy of memory. This is not limited to just simplistic stimuli. We were able to replicate this effect using real-world objects as well as human faces. So far, what we have been talking about is a working memory representation that entered your mental workspace through, if you will, the front door, visual perception. But if you look into psychological theories about working memory, many argue that the working memory also has a backdoor. In other words, information can be retrieved into working memory from long term. Just to illustrate that point, let's consider the following. Imagine that you are casually browsing on the internet and you just run into this really cool looking jacket. In order for you to say, oh, that's a really cool jacket, you need to load that information into working memory so that you can closely inspect the quality of it. And then you're satisfied looking at it and you start browsing again, and now you find this really cool boat. And if you're like me, loving fishing, you might feel like, oh, one day I'll be rich enough to buy this boat, right? I can dream big, right? And after that, you just continue on doing that browsing on the internet for an hour or so. And then you realize, wait a minute, that the jacket that I saw was really cool. I kind of want to buy it. But at this point, what you need to do is to load up that jacket from your long-term memory because it's not in front of you anymore. And then use that memory representation so that you can find it on the internet, right? So what this shows is that, yes, you can load information from long-term memory so that it can guide your behavior. So my student, Joe Saito, he wanted to see whether the information stored in long-term memory is also susceptible to SIMB. To do that, he asked participants to remember 240 pictures of real-world objects, like that jacket, beanbag, notebook, and key, and so forth. After they learned these 240 images, Joe asked participants to perform a retrieval task. In the retrieval task, he presented a grayscale image and asked participants to indicate whether they remember seeing the colored version of it using a varying degree of confidence scale. After they report whether they remember seeing that colored version, we asked participants to report what the color was of that original item, along with the confidence. In the critical retrieval condition called bias condition, after participants indicated whether they've seen that colored version of it, we have people do a similarity judgment by presenting a pair of probabilities. After they judge which one looks more similar to what they remember, then they reported the original one, along with the confidence. Importantly, Joe asked participants to do this retrieval task twice. Once on the same day as the encoding task, but the second time, 24 hours later, the encoding task. Is long-term memory susceptible to SIMB? One way to look at it is to see whether the perceptual judgment that was done after the encoding task biased the long-term memory representation. When we look at that for the day one objects, what we found is a reliable bias in the direction of the item that was judged to be similar. Another interesting question that you could ask is to say whether the delay between encoding and the goal-oriented use amplify the susceptibility to the SIMB. To answer that, he can look at the magnitude of the bias for the item that was used for the comparison on day two. And here what he found was an amplified bias for the item that was used in perceptual comparison on day two than day one. So yes, the delay from encoding to memory usage seemed to amplify that bias. Another interesting question that we could ask is, does the SIMB persist overnight, right? Once you bias your representation, does it stay biased for a longer period of time? One way to address that is to look at the item that was biased on day one and have them recall it on the day two without additional perceptual judgment. And that's what we found. Right? There's no decrement in the magnitude of the bias when the item was accessed again on day two. So SIMB seems to induce a lingering change to the memory representation. One last set of experiment that I like to talk about is tapping into this idea about the retrieval context generalizability. Right? If you encode new information into long-term memory, you often have to retrieve that information in different contexts. If you meet a friend in a classroom, you need to be able to locate that person when you see him in a cafeteria. Right? The long-term memory is excellent in retrieving those information across contexts. So we wanted to see whether this SIMB also happens in a retrieval general manner. To do that, Jarek asked participants to encode something called profile. Profile consisted of a human face along with two attributes, the name of the face and the academic major that this face studies. So we first present our face along with two pairs of attributes, one pair of name, one pair of major. And we ask participants to indicate which one is the correct name and which one is the correct major for this person. Participants learn this iteratively through trial and error by us presenting the feedback. By going through this trial and error learning, participants successfully encoded 8 profiles. Okay? So they learned face in association with name and its major. After that, we had participants do the recall practice task. Here, participants were presented with one attribute, and we asked participants to retrieve the face that went with that attribute. After they indicated how confident they are in retrieving that face, we had participants do a similarity judgment. Ask which one is more similar to the face that was associated with that attribute. And then they would report that remembered face along with the confidence. Importantly, in this retrieval practice task, we only used one of the attributes for each face, right? Either name or major. This way, we were able to save up the other attribute to test the context generalizability of the SIMB. After this recall practice task, we did the final recall task. And here we presented both attributes, name or major, right? And asked them to simply retrieve the associated face. So the recall was prompted using both practice and unpracticed attributes. So let's see what happened. So here what I'm showing you is the bias observed in the recall practice phase. And not so surprisingly at this point, we are able to replicate the SIMB. The question is whether this bias generalized over time to the final recall task and also across the retrieval context to the unpracticed attribute. When we look at the across time generalization, we are able to show that the SIMB induced a lasting distortion. Now the question is, does this effect generalize to the time when you retrieve that face using a different retrieval-cue? The answer was yes. We were able to show that the SIMB generalized to memory retrieval that was triggered by a different retrieval-cue. So just to summarize, long-term memories are also subject to the SIMB when it is retrieved into working memory. It happened with the real world objects and also a human face profile. And the SIMB, once induced, showed a lasting change to that long-term memory. Furthermore, the SIMB seems to generalize across retrieval context. Right? Once your memory representation is distorted, no matter how you access it, that information remains distorted. So to wrap up, in order for us to best understand the goal-directed working memory, it is not sufficient to just focus on characterizing the quality and quantity of information represented in working memory. What we really need to look at is what happens to working memory and how we assess the quality of the representation subjectively, right? Why? Well, at the end of the day, what influences our behavior is our subjective assessment and the usage of that memory representation. Also, to be more specific, comparing working memory representation with subjectively similar inputs risk lasting and generalizing memory distortion, right? We call this a dilemma of working memory because if you want to keep your memory accurately, it's best not to use it, right? But if you don't use the working memory, it defeats the whole purpose of working memory as a goal-directed memory system. Well, this has a significant implication in real life. For example, right, there are many cases in real life we have to rely on the accuracy of memory representation, and to prove that information, we need to ask people to use it in a perceptual comparison. For example, when you have to draw up the picture of a criminal, you often have to do lineups, right? To do the lineup, you need to compare memory representation of the criminal to people who is standing in front of you. Another interesting line of work is to think about different kinds of outcome for this perceptual judgment. Sometimes we think some faces are similar, but other times you may think that the face is the same face, even though it is different, right? Is there differential memory distortion underlying a similar judgment and the sameness judgment? We are conducting line of work examining this difference, qualitative difference that follows similar judgment and the same judgment. Additionally, if you look into a long-term memory literature, there are many other kinds of memory distortion. For example, people sometimes misremember yield sign instead of the stop sign, despite many physical differences between the two signs. The shape is different, color is similar, but the shape is different, and the signs on there is quite different. Is there any way for the SIMB or similar kind to explain this dissociative memory distortion in the long-term memory literature? Additionally, I think it'll be very interesting to examine whether the same happens to other modality of working memory. We know that we can hold information from other senses into working memory, like acoustic information or tactile information. Are they also susceptible to SIMB? Would be a really interesting direction of research, I think. Lastly, what about the lifespan? Pre-COVID, we just started testing the older adults with the same paradigm, and we were able to show that the older adults also exhibit SIMB. Another interesting direction to take is to look at the children, right? Are they also susceptible to SIMB? If so, are they more or less susceptible? I think all these would lead to a really interesting line of work, and we are really interested to follow up on that after the pandemic is all over. On that note, I'd like to thank you all for your attention, and I'd like to extend my thanks to my great students along with the awesome collaborators and my funding agencies. Thank you.